matrix type linear maps, and I call it number 2 because there was already one slide discussing matrix type linear maps, but this one will be quite a substantial development of that slide. So look what I'm talking about when I say a matrix type linear map. Imagine I have a matrix with scalars from the field F. Remember the size of my matrix, m columns and n rows. It's just a quick reminder for you that F basically is one of these number fields, either rationals, reals, or complex numbers. So the matrix type linear map we have discussed with you, it's the one like this. I will call it T sub A this time. So it's a map which depends on the matrix A. In what it does, it maps n tuples into m tuples by simply multiplying n tuples with the matrix A. This type linear map. This type of the linear map we have discussed with you. We proved it is a linear map and everything else. And for the purposes of the current slide, I will call this type 1 matrix type linear maps. It's not an official name. It's just for the purposes of the current slide. Now, the second type I'm going to discuss today on this slide, I'll call it type 2 type 2 matrix type linear maps. This is a lot more general linear maps, and for that, again, I will need two vector spaces. These are my two vector spaces, V and W. Again, my two vector spaces, they just share scalars and nothing else. Now, within these two vector spaces, I will need two bases. Here they are. One of them will be basis B with the vectors v1, v2, and vn. That will be basis in V. And the second one, I will call it W1, W2, Wm with the basis, that will be basis in W. So here's my setting. It's a complete setting. Now look what kind of linear map I will call the matrix type linear map of type 2 on this slide. It will be a map which I will use the symbol T sub ABC for it because it will depend on the matrix, original matrix here. It will depend on both bases, B and C. For different base will be different map. It will map my V into W. And the shortest way to write this map is like this. It will be a map like this. The image of this map on the vector x will have a coordinates with respect to the basis C, such that they are the same as the x coordinates with respect to the B multiplied by the matrix A. It's rather convoluted definition. I mean, if you see it for the first time, and I will take it through it again with the more details. But later on, if I just need a map like that, I will probably just give you this line, and I will be hoping that that line will not be as convoluted as it maybe looks right now for you, because it's the first time you see this definition. So look what happens now on a broader scale. We take a vector from V. We take a vector from V. For this vector first, on the first step, it's like a multi-stage map. We find the representation of this vector with respect to the basis in V space, with respect to this B, which is effectively means we find the coordinates of this vector x with respect to the B basis. That's the first stage of the map. The second stage of that map, it takes this n tuple now and produce a new m tuple by multiplying this n tuple with the matrix A. So by using this map, TA. So we take this n tuple and produce a new m. This time it will be m tuple, which I will use the letter mu for that, mu1, mu2, up to mu m, which is a product of my A matrix, original A matrix from here, and my n tuples from here, like this. And now I take this new M tuple. I take this new M tuple, and I use this second basis to reconstruct the vector. So my T of x now will be a combination of this second basis in the codomain with this new M tuple. Here it is. Mu1 W1, mu2 W2, mu M W M. This single line, which I will use very often in the actually I'm not sure how often I'm going to use it, but I will use it a few times, that's for sure. This single line, it just encodes this lengthy multi-stage mapping. Look at this again. We take a vector from V. First, we represent the vector as a linear combination, so we recover the coordinates of this vector with respect to the basis. Then with the help of these coordinates and with the help of the multiplication, we reconstruct new M tuple. And for this M tuple, with this M tuple, we build a final vector which will be the result of action of my T on X. Free stage map. The reasonable question, of course, will be, is it a linear map? And you may be like, if you just start thinking about how we're going to justify this as a linear map, given that just one action of this linear map takes these three stages, if you just start thinking about checking the A and B properties of a linear map for such three-stage combination, it may seem terrifying, but with the help of what we just discovered before, we can actually do it in almost in an instant. Because these three stages, I can actually write them a little bit shorter like this. My x vector from B taken to the coordinates of this x vector with respect to the B basis, and that's the n tuple with these scalars. Then this n tuple is multiplied by the A matrix, it's the second stage. That will be the M tuple, you see. And then this M tuple is used to reproduce a vector. On each stage, each individual stage, we have a name for that. This is the I sub B map from my previous slide. This is a TA map from the type 1 case. And this is the J sub, well, C, because a new basis, but still it's a map from my previous slide. So in fact, if I use my composition language, my map TABC here, it's a composition of three linear maps. J sub C composed with T of A and composed with I sub B. And therefore the question whether it is a linear map now becomes a trivial question because it's a composition of three individual linear maps. And we know that if we compose a linear map, the result will be a linear map. Here's another diagram which shows how my composition works. So V taken to Fm, to Fn, and for Nicholas, then to Fm for Mary, and to W, and that's my composition. Individual elements of my composition, IB, TA, and JC.